We're going to take a look at rationalizing the denominator. Basically, when you see the word rationalizing, that means get the square root out. So I want to get the square root out of the denominator. And so when I look at number 1, I know that if I were to multiply this by 1, that I didn't actually change it. I left it the same. I've got 5 times the square root of 2, or 5 over the square root of 2. Well, which means that if I can multiply by something that's equivalent to 1, then I'm not really changing it. I'm just rewriting it in a different way, and that's what we want to do by rationalizing. Okay, we want to change it so that it just doesn't have the square root of 2 in the bottom. We still want it, if I were to type it in the calculator and do 5 divided by the square root of 2, I still want whatever I change it to come out to be that exact same decimal that happens to come out when I do the first problem. Okay, I don't want the answer to change, I just want it to look different. And so that's what rationalizing the denominator does. So I want to get rid of the square root over 2 down here. Now, we all know that if I were to take something like, let's say, 12 divided by 12, that's equal to 1. And something like negative 2 divided by negative 2 is also equal to 1. So if I take the same thing on the top and the same thing on the bottom, then I'm really just doing a different version of the number 1. And so in the case that we had a square root of 2 in the denominator. That's what I wanted to get rid of. So if I did the square root of 2 over the square root of 2, that is still a 1. It's the same thing divided by itself. No matter what I do, even if I did x divided by x, that's a 1. Okay, and x to the third divided by x to the third, that's a 1. Anything divided by itself gives me a 1. So when I go back here, if I were to multiply by the square root of 2 over the square root of 2, I'm actually not doing anything because I'm multiplying by 1. And so on top, I've got 5 times the square root of 2. And on the bottom, I've got the square root of 2 times the square root of 2. Well, we did some work with that already. The square root of 2 times the square root of 2 gives me the square root of 4. On top, I leave that the same. On the bottom, 5 times the square root of, the square root of 4 on the bottom actually is the number 2. And so I no longer have a radical in the bottom or the square root in the bottom. And so I'm good to go with rationalizing the denominator. They're not always going to be that easy, but that's kind of the idea behind all of them. So let's look at number 2. I want to see what I can multiply this by so that I can rationalize the denominator. What I need to get rid of is the square root of 5. The square root of 5 can't be down there. So what I'm going to do is I'm going to multiply by an equivalent of 1, but get rid of that square root of 5. So on top, I have 4 times the square root of 5, which is 4 square root of 5. And then the square root of 5 times the square root of 5 is the square root of 25. But hopefully you can see a shortcut kind of working here, that when I have the square root times itself, they actually cancel each other out, and the square root just goes away. So I get the square root of 25, which is 5. So you are able to hopefully skip a step in the middle there if you understand what's happening. If not, just multiply those things together, and that's fine too. So let's go a little bit farther down, get some problems that are a little bit tougher. First of all, let's take a look at number 4. When you put that negative out front, doesn't really do much to it. It just makes the answer negative, so it keeps the answer negative when you're looking at it. Let's take a look at number 8. So again, I want to get rid of the square root of 3 at the bottom. That's what my goal would be. So I'm going to multiply by the square root of 3 over the square root of 3. That was a horrible square root. And so I'm multiplying by the number 1, which doesn't really change it. It just changed the way that it looked. On top, instead of me having just a number times the square root of 3, I actually have two things multiplied. So I have the square root of 12 times the square root of 3 is the square root of 36, 12 times 3. And on the bottom, I have the square root of 3 times 3, which is the square root of 9. And the square root of 36, that's a 6. The square root of 9, that's a 3. And I actually can continue here. 6 divided by 3 actually gives me a 2. Okay, so you want to keep going as far as you can. So if I typed in the square root of 12 divided by the square root of 3 on my calculator, I should get a 2 back. It should come back that way every single time. Going down a little bit farther, let's take a look at number 13. Hopefully by now you know that I need to multiply by a square root of 2 over a square root of 2. But when I do that on the top, I get 4 times the square root of 5 times the square root of 2, which is the square root of 10. And then the square root of 2 times the square root of 2 on the bottom gives me the square root of 4. So I have 4 square root of 10 over the square root of 4 is a 2. And I can reduce that too. 4 divided by 2 gives me a 2. 2 goes into there twice, and 2 goes into there once with the square root of 10. Do not reduce the 2 with the square root of 10. You cannot do something that's outside of a square root and reduce it with something that's on the inside of the square root. Okay, and we look at this in 2 stages. You have the outside, something that's outside the square root, and something that's inside the square root. We can multiply things that are inside the square root. We can multiply things that are outside the square root. We can't multiply things that are outside with things that are inside without that square root being a separator. So I end up with 2 times the square root of 10 for number 13. Let's take a look at the back. So same idea, the negatives don't do a whole lot here, but let's take a look at number 20. Number 20, I want to multiply by the square root of 7 over the square root of 7. So on top, I get negative 2, and then the square root of 10 times the square root of 7 is the square root of 70. And then on the bottom, the square root of 7 times the square root of 7, hopefully you can make this jump already, is going to give me a 7. Well, the square root of 70 looks like a pretty big number, so I want to make sure that I don't have any perfect squares in there to reduce. And so when I do that, I look at the square root of 70 and I say, well, 70 is 7 times 10, and 10 is 5 times 2. There are no pairs in there. There's no perfect squares that would reduce, and so I end up with that being just the answer. However, what happens when I look, let's say, at number 24, I get the square root of 10 times over the square root of 10 is what I want to multiply by. On top, I get the square root of 140. On the bottom, I get the square root of 100. Well, the square root of 100 is the easy part. That's just 10, and some of you probably could have made that jump already. The square root of 140, again, I want to look to see if there's anything that I can reduce that by. Okay, so we're looking for perfect squares that are in 140. So we start looking, well, I know that 140 can be divided by a 2, and so if I know that 140 can be divided by 2, then I get a 70, which also can be divided by 2. That means that 140 could also be divided by 4. So I could write this as 4 times whatever 4 times 35 then is going to give me 140. So I can reduce this. I can do the square root of 4, which is a 2. The square root of 35, well, 35 can't break down. That's just a 7 times a 5. There's no perfect squares in there. And then that's still over 10. Well, now I can reduce the 2 that's on the outside with the 10 that's on the outside. 2 goes into 2 once and into 10 5 times. So I end up with 1 times the square root of 35. You don't have to put the 1. You can have a lazy 1 there, divided by 5. Do not divide the 35 by 5. 35 is under the square root. The 5 is not under a square root. Okay? Inside-outside idea. So that kind of leads us back into a little bit of review here. Going with adding and subtracting these. So number 27, let's take a look at. We want to break down, some of you are writing it like this. I want to break down the square root of 20 into 2 numbers, one that's a perfect square and one that's not. And so that's perfectly fine. 20 is 4 times 5, and 4 is the perfect square. So I get 6 times the square root of 4, which is actually 6 times 2 times the square root of 5. So that's 12 square root of 5. And then I continue with the minus 2 square root of 45. I want to multiply that or break that down into 2 numbers, one being a perfect square. And again, 45 is 9 times 5, so the square root of 9 is our perfect square. So I get 2 times the square root of 9 is 3 times the square root of 5, which gives me 2 times 3 is 6 times the square root of 5, not 3. And now I've got those two radicals are the same, so 12 square root of 5 minus 6 square root of 5, it gives me 6 square roots of 5. And so adding and subtracting, they have to have the same exact radicals in order to continue with them. And then the last part here, multiplying these radicals. Let's take a look at the last one, 32. Again, this is the idea of outside-inside radicals. So outside the radicals, I have a 5 times 6, which is 30. Inside the radicals, I have 6 times 3, which is 18. Don't stop there. I've got the square root of 18. I want to try to break that down. So I've got the square root of 18. I want to break down into two different square roots. 18 is 9 times 2, and 9 is my perfect square. So I've got 30 times the square root of 9 is 3, times the square root of 2. 30 times 3 is 90. And I end up with 90 square root of 2. 90 square root of 2. And again, if you were to type in 5 square root of 6 times 6 square root of 3 and you were to type it in the calculator, you should get the same exact answer at the top as a decimal as you would get as multiplying or putting into the calculator 90 times the square root of 2. It should come out exactly the same. We're not changing the problem, we're just rewriting it in a different way.